Hi, I'm Robert Mars, Principal Solutions Architect on the Alexa Voice Services team at Amazon. I'm also the Voice Interoperability Initiative Device Hardware and Software Lead at Amazon. And in this presentation, I'll provide technical insight into the VII Multi-Agent Design Guide created in collaboration with VII members. When I mention VII in this presentation, I'm referring to the Voice Interoperability Initiative. What can you expect to get out of this presentation? You'll learn about the benefits of supporting multiple voice agents on products, how to make multi-agent experiences delightful, gain familiarity with the Multi-Agent Design Guide, and learn about multi-agent technologies from Amazon. In September of 2019, Amazon announced the Voice Interoperability Initiative with over 30 member companies. The Voice Interoperability Initiative is about members working together to ensure that products with multiple voice agents operate seamlessly and provide customers with choice and flexibility. Today, VII has over 75 member companies. What lies in the future for multi-agent devices? People will come to know multiple voice agents on devices as providing different services much the same way they know to call a plumber for plumbing work and an electrician for electrical work. Multi-agent design presents new frontiers in privacy, cognitive load for customers knowing which agent to use for what, and interoperability of agents working together. How do you get a head start? By starting with the Multi-Agent Design Guide. Together with feedback from VII members, Amazon developed the Multi-Agent Design Guide to provide design recommendations that product and agent developers can use when designing and building multi-agent devices. The Multi-Agent Design Guide was publicly announced on September 9, 2020. The Multi-Agent Design Guide principles are founded in privacy, predictability, and ease of use. When customers interact with multiple agents, it's important that they're provided with transparency in their experiences. Voice agents should interact in expected and familiar ways, and customers should be able to easily interact with agents on the device. I'll next illustrate some of the benefits of multiple voice agents on your products. Here we see the benefits of two different voice agents named Carly and Alexa built into a car's head unit. Carly is an imaginary agent. Carly, roll down the windows, is one of many commands Carly supports for functions in the car. Alexa offers customers many choices in music service providers. Alexa, set the volume to 10, is a way to tell Alexa to crank up the music volume. Together, Carly and Alexa increase the features and functionality in a single device for the car's occupants. Here's an example of another agent named Spresso, which co-resides with Alexa on an espresso making device. Spresso is a specialist agent, a coffee sommelier of sorts with unique capabilities. Together, Spresso and Alexa complement one another and increase overall functionality for customer delight. Next, I'll cover multi-agent wake words, the attention system, universal device commands, and agent transfers. Let's start with multi-agent wake words. The Multi-Agent Design Guide tells us that multi-agent wake words on a device should sound distinct and be easy to remember. Wake word engines use machine learning models to recognize wake words. Wake word engines aren't perfect. Wake words that sound the same are hard to distinguish. When a customer speaks a wake word, they expect the device to only send their voice audio to the wake word agent's cloud services. Let's see some examples of how having distinct sounding wake words enforces privacy and avoids customer confusion. Here are two wake words for different agents named Lexus and Alexa. Individually, they sound great. However, they sound similar. Lex is common to both Alexa and Lexus. Let's see what happens when we say Lexus and Alexa on an Echo spot that only supports the Alexa wake word. Lexus, what time is it? Alexa, what time is it?
It's 7:47 a.m.
We just saw how Lexus wakes the Echo Spot, but it got no response. The light ring briefly showed purple. This is because Lexus failed Alexa cloud-based wake word verification, which verifies the wake word with greater accuracy. The voice audio asking for the time was never sent to the Alexa cloud, and customer privacy was preserved. What this tells us is that combining two agents on a device with wake words Lexus and Alexa is problematic and not a good idea. Here are some examples of distinct sounding wake words for multiple agents on a device. Computer and Alexa, Carly and Alexa, Espresso and Alexa. And they're all easy to say and remember. Let's see a demo that shows how these other wake words do not wake the Alexa agent on the Echo Dot. Computer, Carly, Espresso, Alexa, never mind. We just saw how similar sounding wake words can wake the incorrect agent and potentially result in the customer's voice audio going to the wrong agent. Next, I'll show how the presence of another agent's wake word in an agent inquiry can result in portions of the voice data being sent to the incorrect agent when not properly handled. Back to the car agent example, Carly and Alexa. Alexa, who gives better driving directions, Carly or you? Both questions are intended for Alexa. However, notice how Carly is spoken in the second question. Speaking Carly will trigger the wake word engine. It's up to the device software to ignore that trigger in this example. Let's explore what happens when it doesn't. Here the Alexa and Carly wake words and utterances are annotated. An utterance is the speech that follows a wake word. Something unexpected happens here. Alexa, who gives better driving directions, streams to the Alexa cloud services, and Carly or you streams to Carly's cloud services, which is a privacy violation. The customer had no intention of Carly waking or having their voice audio streamed to Carly's cloud services. And it doesn't end there. Alexa responds with, "I'm sorry, I didn't understand that." Carly responds at the same time with, "I didn't understand that." And both are output at the same time, resulting in garbled audio output. The multi-agent design guide addresses this issue in the following way. When one agent has been invoked and is actively streaming an utterance to the cloud, no other agent's wake word should invoke that agent. Let's see how this is handled. When does an agent actively stream an utterance to the cloud? While it's in the listening state. An agent interaction typically involves 4 states: idle, listening, thinking, and speaking. After a wake word is detected, a device enters the listening state and starts streaming voice audio to the agent's cloud services. The device enters the thinking state when the cloud services start processing the voice audio. It next enters the speaking state while the agent responds. Customers need to know when and to where their voice audio is being streamed. When a customer starts an interaction with an agent on a multi-agent device, they may suddenly realize that they've called upon the wrong agent after saying its wake word and want to bail out. Alexa provides a couple of ways to bail out. One is to say nothing after the wake word and wait for a timeout. Or another way is to say never mind to instantly return to the idle state. They may then invoke the other agent by saying its wake word. Here's a simplified diagram showing multi-agent wake word handling for a single wake word engine. The customer on the left speaks into the microphone. Their voice audio is sent to the wake word engine. Only Alexa or Carly can trigger the wake word engine. And when either wake word is spoken, the wake word engine detects it and notifies the client software, which then starts streaming the voice audio to the corresponding agent's cloud services. Conceptually, the red latch in this diagram can move up or down to channel audio to either agent until the agent enters its speaking state or returns to its idle state. Why wait until the speaking or idle state to invoke another agent? The active agent is not listening when in those states, and it allows another agent to safely enter its listening state. Using this approach prevents voice audio from routing to the incorrect agent and enforces customer privacy. Let's have a look at a demo that shows proper handling of the other agent's wake word in the utterance. Here I have a Raspberry Pi 4 with a SenseHat LED array that shows the active agent's various states, listening, thinking, and speaking. I'll be putting a pair of sunglasses with polarizing lenses over the LED array so that it's visible during interactions. Computer, what can you do that Alexa cannot?
You can ask me questions about my hardware, software, and operating system. I can also answer many questions about my setup and configuration.
Alexa, are you a computer?
I like to imagine myself a bit like an aurora borealis, a surge of charged multicolored photons dancing through the atmosphere.
Also notice the LED array visuals where both agents use consistent but slightly different patterns for the listening, thinking, and speaking states. Note how computer, what can you do that Alexa cannot, embedded the Alexa wake word but did not activate Alexa. Likewise, in the request for Alexa, where stating computer in the utterance did not activate the computer agent. In both cases, customer privacy was preserved. Next, I'll cover the attention system for multi-agents. The attention system conveys an agent state, which agent is active, as well as device states, using visuals and audio cues. Let's have a look. A multi-agent attention system consistently conveys an agent's idle, listening, thinking, and speaking states, as well as device states like microphone on or off. There can also be other attention system states. Alexa includes several, such as for notifications and timers. A consistent attention system is essential for multi-agent scenarios to avoid confusion and provide transparency, and to convey which agent is listening and speaking through distinctive visual and sound cues. The multi-agent design guide tells us that all agents should convey listening and speaking states, thinking state if applicable, and mic on-off state, and have non-conflicting visuals and sound cues. For example, show the mic off mode in red universally for all agents on the device for consistency. Let's see a demo of non-conflicting visuals in an attention system for multiple agents. Computer, what can you say?
You can ask me questions about my hardware, software, and operating system. I can also answer many questions about my setup and configuration.
Alexa, what time is it?
It's 12:33 p.m.
Great! Those polarizing lenses are still covering those ultra-bright LEDs. Next, I'll cover universal device commands. What are universal device commands? Universal device commands are words that can be spoken to any agent to perform a common function. Here's an example of a smart appliance, such as a microwave, with built-in multiple agents, where its timer goes off. Imagine that you just walked in the kitchen when the timer goes off, but you didn't see it get set. It may not be obvious which agent was used to set the timer. Which agent do you call upon? When agents implement universal device commands, they don't have to know which agent set it. You can ask any agent to stop the timer. Regardless of which agent started the timer gets turned off. It should not result in an agent telling us that no timers are set. Another example is volume control. Any compatible media playback agent should be able to support universal device commands for volume. Let's next see a demo of universal device command handling, where setting a timer for 5 seconds can be stopped by a different agent when it goes off. Alexa, set a timer for 5 seconds.
5 seconds, starting now.
Computer, stop. Cool. There are two types of universal device commands: device global and cross agent. Controls on a device, such as volume control, have device global commands. Another example is skip or pause, such as might be found on a remote control. Device global commands often have physical counterparts. Cross-agent commands are commands executed by an agent, such as a reminder, where there typically isn't a physical counterpart to control the same function. Here are examples of device global and cross-agent commands depending on whether the device also provides controls to perform the same function. A multi-agent device should consistently support a universal way to stop or dismiss timers, alarms, and reminders for all compatible agents. A compatible agent is one that also supports a common feature. Likewise, universal device commands should be used for stopping media playback or camera feeds, as well as rejecting incoming calls if the device supports calling. Here are universal device commands that multi-agent devices should consistently support. Stop speech, where a person says the agent name followed by stop. A global foreground stop is one that applies to current activity on the device, such as music playback or a news briefing. And similarly, volume controls should be defined in consistent ways for controlling the speaker's volume. Multi-agent devices should provide access to device state information. For example, volume control or heat setting. Agents invoked to take action on an ongoing activity should only use the device state information to fulfill the request. For example, one agent is asked to set the volume to level 5, a user then manually sets the volume to level 3, an agent is then asked to raise the volume, it checks the device state's volume level, and then increments it. For agents invoked to take action on an ongoing activity that was started by another agent, only the minimum data needed to complete the request should be shared. For example, Agent A is asked to set an alarm, which it sets. The alarm then sounds. Then Agent B is asked to turn off the alarm. Agent B queries the stoppable activity on the device and then stops the activity, not even knowing it was an alarm. Agent B has no context of the activity that was started by Agent A. Next, I'll talk about agent transfers. What's meant by agent transfer? An agent transfer is where an agent is aware of another agent on the device that may be able to fulfill the request. I'll cover two different types of agent-aware transfers. One is a dead end, where the activated agent mentions the other agent might be able to handle the request, and that's all that it does. The other is summoning, where the activated agent makes the same mention, but also wakes the other agent. The customer does not need to say its wake word. Let's see a demo of a dead-end agent transfer. Computer, who won the Red Sox game?
I do not know about that. Try asking Alexa. She is a much more knowledgeable computer than I.
Notice how the computer agent did not automatically engage Alexa. In this dead-end use case, the user is required to have to speak the Alexa wake word and repeat the same question. Here's an example of the agent transfer type known as summoning, where the called-upon agent summons the other agent to handle a request that it cannot. These two agents in the example will be Alexa and Carly. A user asks, "Alexa, how do I open the door?" Alexa responds with, "I don't know, but Carly might." Carly then responds with, "Carly here, how may I help?" The user then asks, "How do I open the door?" And Carly responds with, "Release the child lock and then pull the lever." Notice how there isn't a need for the user to say the summoned agent's wake word. Let's see a demo of agent summoning.
Computer, remind me to pick up my dry cleaning at 5 p.m.
That sounds like something Alexa can help with.
Hi, Alexa here. How can I help?
Remind me to pick up my dry cleaning at 5 p.m.
Okay, I'll remind you at 5 p.m.
Note how, although the user didn't have to say the summoned agent's wake word, they did have to repeat the utterance. In this case, they repeated, "Remind me to pick up the dry cleaning at 5 p.m. Why is it necessary for the customer to repeat the utterance? Because it avoids inadvertent transfer of the utterance to the incorrect agent. Also note how the greeting prompt, "Alexa here, how may I help?" by the summoned agent makes clear which agent the customer is speaking to. No voice audio has transferred to the summoned agent up to that point in time. Using this technique ensures customer privacy and avoids confusion as to which agent the customer is speaking to. Here's a demo that combines summoning an agent and a universal device command.
Computer, set a timer for 5 seconds.
That sounds like something Alexa can help with.
Hi, Alexa here. How can I help?
Set a timer for 5 seconds.
5 seconds, starting now.
Computer, stop.
The timer gets set with Alexa, but is stopped using the computer agent. Given the short delay of the timer and how the user started the conversation with the computer agent, it stands to reason they should be able to ask the computer agent to stop the timer, even though it was set by Alexa. User interactions with devices have temporal dependencies. Here's what the MultiAgent design guide has to say about agent transfers. Summon the other agent if it's capable of handling the request. Repeat the request to the other agent without the wake word. Avoid passing data or context between agents during the transfer. This guidance makes it easy to reinforce customer privacy. Automatically transferring voice data intended for one agent to another agent risks violating the data privacy of the customer or another person speaking in the background. Thank you all for attending this presentation on technical insights to the MultiAgent Design Guide. We've covered some of the benefits of supporting multiple voice agents on your products. We've explored ways to make multi-agent experiences delightful for your customers through baseline guidance and recommendations. And we covered some of the principles of multi-agent design and Amazon technologies for enabling multi-agent product development. I thought I'd take a moment to address some frequently asked questions. Does Amazon Engineering believe that standard acoustic echo cancellation system design will handle the case of Agent 1 speaking to Agent 2's wake word? We recognize that acoustic echo cancellation's ability to remove text-to-speech from the audio output path and wake word engine detection sensitivity for wake words will vary across vendor implementations. The Multi-Agent Design Guide provides guidance to ignore other agent wakes when an agent is in its listening state. Do we need a registry and/or a governing body that can make sure wake words are distinct? A registry and/or governing body to make sure wake words are distinct should not be necessary because multi-agent device makers can easily perform their own verification of agent-wake word combinations. Generally, wake words that do not sound similar to people will be distinguishable by quality wake-word engines with mature wake-word models. When a customer uses an action button, the product may decide which agent will respond. Any thoughts around how the product makes the determination of who should handle a request? The MultiAgent Design Guide discusses the need for mapping a single multi-mode action button or multiple action buttons to individual agents so that the customer will always know which agent is invoked. Also, the attention system should always make clear which agent a customer is interacting with at all times. Okay, that's it for Q&A. Here are links to additional information on the MultiAgent Design Guide. Once again, thank you all for attending this presentation on technical insights in the Voice Interoperability Initiative MultiAgent Design Guide. I hope it's been very beneficial for you. Happy multi-agent product building.